All right, so I'm doing this is video 2-1 energy. I'm a little bit late to this, but got to get them done. We're gonna do web assign 18, number 18 from I think it was 4A, and yeah, this is energy, linear energy. So here it's asking inclined plane has spring theta angle 20, has a spring force constant K 485 Newton over meters. I'm also just gonna do this instead of just doing it and then explaining because I kind of don't remember how I did this, so I'm just gonna work with it. Parallels of the surfaces figure below, mass shown, and we go. Okay, so we know that. Hold on. So we know that mass equals 2.67 kilograms. We know the distance from the spring from this position shown. So distance here is D equals 0.297, 0.297 meters. So what we're looking for is the distance the distance spring is compressed, so like around this. We'll call this x, delta x, I guess. All right, so first we will get our system, circle our system, which is here. We know that we're going to call we're going to make this our coordinate axis here. Then we're going to make a free body force diagram. I'm going to rotate it so that, and we know that, theta equals 20 degrees. I'm going to rotate it so we know, so normal force is pointing up. So normal force, we'll call here normal force, and we know force of gravity will be at a 20-degree angle. So I'll just we'll call this a 20-degree angle, because why not? Force of gravity. So we know this is FG sine 20 degrees. This is 20 degrees theta. And this is FG cosine 20 degrees theta. All right, so from here, so it is, we have the velocity pointing down the ramp. And since, momentarily compressed. Okay, and so we will have acceleration going downwards as well. Same way as velocity. And so, because we're assuming this is frictionless, I think, right? Sure, we'll say it's frictionless, I think. All right. We have velocity, acceleration this way. All right, so now we know that since we're not looking for normal force or the y component because they're balanced out, we know that it's 0. So we're going to be looking for the net force on the x plane. So we know that the force we're going to need to use is here, FG sine 20 degrees. So we're going to need our net force to equal FG sine 20 degrees. And for FG, we know FG is mg, so we'll just rewrite it as net force equals mg sine 20. And then, so what we are looking for, we're going to have to use energy, obviously. So we will, okay, so we'll use kinetic energy. We'll come back to this right here. So we'll do kinetic energy. We'll call this KE. Why not? K equals 1/2 mv squared, as we know. And here we know, I think we know the mass. Yeah, mass is 2.67 kilograms, and the velocity is here 0.75 meters per second. So we'll plug this in. Equals 1/2 times 2.67 kilograms times 0.75, 0.75 meters per second squared times 0.75 squared divided by 2. So we have kinetic energy is equal to 0.751 joules. So now what we're looking for, all right, so bear with me. I'm trying to remember this problem. Okay. So I think what we're going to have to do is kinetic energy. We're going to add the work done by gravity. We'll just call that WG, work done by gravity, plus work done by gravity. And then Then we have to subtract works by spring, because that's when the spring compressed and it'll come to rest fully come to rest. So that means since it comes to rest, we know that it'll be 0 joules after it's gone through this work. Let me make sure. Yeah, microphone's on. So we have 0 joules. So we know that kinetic energy is 0.751 joules. We know that work done by gravity will come back here. Work done by gravity, we know that work of anything is equal to net force times displacement. So we'll call work by gravity. The force here is mg sine 20. And then we'll call displacement. We have here distance is 0.297 meters, and that's just this. So we know that we're gonna need this also, delta x here. So we'll call that, I guess we'll call that, hold on. We'll call that d, which is what we have, plus delta x, which is what we're looking for, which is here, delta x. And then, okay. So we know here, work by gravity is, sorry. Here, I'll rewrite this a little bit. So we know work by, actually no, I could just plug it in through here. So we know work by the spring, which is the spring constant. We can call that as work spring. Here, I'll do a different color. Work spring equals 1/2 k delta x squared. Delta x, remember, is this delta x right here. So I can actually, delta x, style, make this red too. All right, so we know delta x is what we're going to be looking for with this work by spring, or displacement with the spring constant here. And so here we have let me rewrite it right here. So we have kinetic energy, which we know is 0.745 joules, plus work by gravity, which is all of this right here. So I can actually just duplicate this over here. So we have this, then we're going to do minus the work by spring, which is 1/2 k x squared. So we have 1/2 k delta x squared, which is going to equal 0 joules. So I can expand this. So we'll have 0.795 joules plus, and we'll do mg d, distance, times sine 20, plus mg delta x sine 20. I want to keep this delta x red because that's what we're solving for. Okay, then minus 1/2 k delta x squared, and that's going to equal 0 joules. So, and I'm pretty sure here we could just, yeah, so here we know the spring constant, so we could just plug everything in. All right, so we'll have 0.795 joules plus m, which is 2.67 kilograms, times force of gravity, 9.8 newtons per kilogram, times sine 20, times the distance, 0.2297 times 0.297 meters, times the sine of 20 degrees. And then we'll do plus mass again, which was 2.67 kilograms, 2.67 kilograms, times force of gravity, 9.8 newtons per kilogram, times delta x, which is what we're looking for, delta x, times sine 20 degrees. Sorry, let me, hold on. We'll move this right here. Well, I should move this further, more space. So then here we have minus 1/2. I'm going to make that a 0.5. 0.5 times spring constant we have is up here, 485 newtons per meter. 485 newtons per meter times delta X squared. It's going to equal 0 joules. Let me do a little bit of, I can't see. 2.67 times 9.8 times 0.297 times the sine of 20. 2.65, let's add that to 0.795. So we have 3.453 joules plus 2.67 times 9.8 and then times sine of 20 degrees, 8.949 delta X minus 485 times 0.5, which is 242.5 delta X squared equals 0. I'm just going to rewrite this really quick. 0 joules. So we'll do 242.5. I'm just going to make this positive. Delta X squared minus 8.949 joules. Sorry. Joules. Who cares about units? It's all a hoax. Minus 3.453 joules equals 0. Plug that into quadratic. I'll just show it here. So we'll have delta X equals negative B 8.949 plus or minus square root of, that is, hold on, 80.09 minus 4 times A 242.5 times C, which is negative 3.453, all over 2 times 242.5. Let's see how this solves out to. So I'll just plug in the big equation. I just showed that one so you can see. Minus X minus equals 0, X. So we have here that delta X equals negative 0.1023 meters, or 0.139 meters. And since it's displacement, we can't have a negative distance, so I think 139, 138, close enough. Yeah. Yeah, that's it. It's a problem.